This is the second in a series of two BME 271 lectures on BioMEMS and Microfluidics. First, we'll continue our discussion of MEMS devices, continued from the last lecture. The acronym MEMS stands for Microelectromechanical Systems, and these are devices that are fabricated using the same kinds of technologies that are used in integrated circuit fabrication. So they essentially are a descendant of that, a new application of those, of things like of deposition onto substrates, patterning, by photolithography, and etching, etc. MEMS systems can sense, control, and actuate things on the micro scale. They can be made very small to sense parameters and actuate things on the micro scale. And if you put enough of them together in an array, then you can start to generate effects on a macro scale, a larger macro scale. So BioMEMS, when we speak of BioMEMS, we're talking about biomedical applications of MEMS devices. As we discussed last time, in the last 50 years or so, we've seen our abilities to build very small electrical things increase exponentially. We can build them far more densely than we could just 10 years ago. So we talked about Moore's law in particular that predicted the rise of the increase in the density of chips of transistors that we could put in a given unit space. So back early on, we've had these four different levels of density of integrated circuits, of transistors and integrated circuits. So the first one they called small scale integration, where you had roughly tens of transistors per chip. Probably they didn't call it small scale integration back then, but that was a post hoc name. Then moved on in the late 60s to medium scale integration, where they were able to fit hundreds. And then this grew exponentially in the 70s. So these are increments of roughly, less than 10 years each. Then we got to thousands of transistors, and then we had VLSI come out in the 80s, where we were then able to set about 100,000 transistors per chip, and this law continued to expand, so that in 2009 we can now fit several billion transistors on a chip. And I don't know that there even is a name after VLSI that has been given to this ability. At the same time as we were making these advances in constructing dense integrated circuits, the knowledge we needed to build very small mechanical devices was also building up, and the convergence of these two knowledge sets and skill sets resulted in 1974 in the first pressure sensor being constructed using MEMS technology, and was actually commercialized by National Semiconductor. And so it, of course, it also incorporated sophisticated circuits such as temperature control circuits, bridges, and amplifiers that were all built into this single chip. And also, as we saw last time, the construction of MEMS devices involves a series of pattern transfers via, for example, for the most part, lithography, or photolithography, material deposition, for example, by chemical vapor deposition, and material removal via, for example, chemical etching. So what we do is we put down some material that's in, so the substrate is the gray here, the material we want to pattern is in green, and then the photoresist that we have patterned already with the photolithography is the red bits there. Then after we have patterned and washed away the photoresist, then we can etch the material to get rid of, we apply a chemical etch usually to get rid of the unwanted material, the unwanted deposited material, and then we can wash away the photoresist to get the pattern that we wanted. And so again, here's an example of one of the more common deposition techniques, which is called chemical vapor deposition. So the idea here is that we have this substrate onto which we want to get something. We want to put some get some film of thin film of a new material on here. So what happens in chemical vapor deposition is that you use a gas phase precursor of the element to be deposited. In this case, the element to be deposited here is silicon dioxide, and so you use this silane gas as your source gas. That precursor gas then reacts in this hot reaction zone and decomposes the material onto the substrate to produce the desired composite material on the substrate. And then the gaseous byproducts are ventilated away. And again, last time we gave the analogy of the form of this process is that it's like the formation of a soot, the black kind of soot that you see on a cool object. That you, like if you take like a piece of metal and you put it in a flame, you start to see this soot deposited on the metal, and this is the same effect. We also talked about once you've got your patterned photoresist on top of your material, you need to get rid of it, right? So you do that by what's called etching usually, and so we have illustrating here isotropic etching versus anisotropic etching. So for example, here in an isotropic etching, you'd actually get these rounded cuts underneath. If you have the chemical etch degrading uniformly in each direction, then you'll have some undercut underneath the photoresist that would be undesirable. So a lot of effort has been put into developing silicon etching techniques, which can give you anisotropic etches, so that you get a much faster etch in one direction than in the other. So for example, in this case, we're illustrating one. Let's see, this silicon etch, this potassium hydride. Hydroxide silicon etch, which is a wet etchant, can go 400 times faster in this vertical direction than it will etch in the lateral directions. So the advantage of this, of course, is that we can get much more vertical kinds of walls in our devices. So again, unlike microchips, MEMS devices require the development of elevated structures, right? Microchips all have devices laid flat on the substrate. So how do we make these, how the heck do we make these elevated structures? Well, to create suspended structures such as wires for a wire anemometer, right? Remember that's a flow sensor that we talked about previously. We need to deposit and pattern a so-called sacrificial layer, on top of which we will deposit the materials comprising the suspended structure. That will then be eroded away, and which will then be eroded away underneath that structure. So for example, what we do is we put this, first we would deposit an insulating layer, for example, then we deposit and pattern a sacrificial layer, right? This is a silicon oxide layer, and then we put down the material that actually forms the structure that we want to maintain. Here's the polysilicon. And then we selectively etch the sacrificial layer, this layer, to get rid of it, leaving the suspended structure in place. And so there's all kinds of tricks that investigators have developed to do this. So MEMS devices can be used for both sensing and actuating. So a sensor is something that detects a stimulus and conveys some electrical signal carrying the information of that stimulus. So for example, lots of MEMS devices, MEMS sensors are things like accelerometers, pressure sensors, flow sensors like the anemometer we just mentioned. And actuators are things that receive some instruction from externally, usually via some electrical means, and perform some desired act. So for example, we have things like MEMS motors, MEMS pumps, and also movable mirrors like this DMB Texas Instruments display. And interestingly, this display happens to be this fancy projector device that looks set to replace the use of chrome masks for lithography. So we may, in several years, never be using chrome masks anymore for lithography, which would dramatically improve the speed with which new masks could be made. So it would be a device, it's very meta like that, though. It would be a device that's made using advanced lithography techniques that itself fundamentally enables advanced lithography techniques. An accelerometer, of course, is one example of a MEMS sensor. So here is a case that we've talked about previously, a type of accelerometer that we've talked about a little bit previously, but not in the context of it being a MEMS device. So here's an inertial mass. It's essentially made of this inertial mass here that is attached to the substrate via these flexible spring legs. So the mass is allowed to move left-right here in response to some acceleration. And then you have these interdigitated stationary fingers that are also attached to the substrate. So the black dots indicate where they are anchored to the substrate. And as the mass moves, it's going to, the distance between these interdigitated, these digits here and the stationary conducting fingers is going to change, right? So you can imagine then that the capacitance between pairs of these fingers is going to change as the mass moves, and you can use that to detect the displacement of the mass, and from that then infer its acceleration. And here's another example of a gas flow sensor made using MEMS techniques. And so what we have here is essentially a membrane, or a membrane comprising these thermo elements that are heated up, and then as gas flows over them, they lose some of their heat, and so you can detect the change in resistance, as we talked about previously with wire anemometers. You do the same thing here as a means of detecting the flow of gas through across them. And here's another view where on one side you have the gas inlet coming in, then you have this suspended membrane here. That's what we're looking at here from, if we're looking at it from the bottom, that's what we have the view on the left here. And so it's suspended over this cavity, and then again as that gas comes through, it sucks away heat from the wires and changes their resistance. So we just talked about sensors. What about actuators? So an actuator is something that converts energy of one form into mechanical energy. So there are electrostatic actuators, chemical actuators, thermal actuators, pneumatic, hydraulic, and piezoelectric are the major types. So one of these types of actuation is electrostatic actuation, and this is based on the attraction between two oppositely charged plates. So here's an example of that, where we have this device when there's no charge across it, or when there's no potential difference between the end of it and some plate on the bottom here, then you have it sticking up like this. It's manufactured so that it ramps up, or it's always sticking up when there's zero voltage across it. And then when you apply a voltage difference between the device itself and the substrate, then it gets pulled down to the substrate, right? And so this is based on, so then these devices are called electrostatic cantilever actuators, and essentially what happens is that an applied electric field produces a deflection of a cantilever beam. And so here's one specific example of an application of one of these, why you'd actually want to do this. So here's an example of one of these devices where it's carrying a mirror on the end of its tip. So when you apply the voltage across it, the mirror moves down, so it's out of the way of this it's out of this optical path, and when there's no voltage across it, it pops up in the way of the path and sends the beam a different direction. So here's an example of a thermal actuator. These are also called BiMorphs. So the idea is that you have these two materials with different thermal expansion coefficients, and when you put a heating current through them, they're going to expand at different rates. And so then material 1 might expand less than material 2, and so you'll get the two devices curling up as you heat them up. And these switches can be done pretty quickly, actually, on the order of 3 milliseconds. So at these very small scales, as I said before, for example, these thermal BiMorphs can switch on the order of 3 milliseconds, which is really, really fast. So you might not expect a larger scale device to be able to switch so quickly. So that's one example of how we have to think differently when we're working with very small devices. So some of the concerns or advantages we have to think about relate to things like inertia. So for example, micromachine components have super low mass, right? And so then rotating components like a little disc or something that you rotate up and down will start and stop essentially instantaneously, so the friction will stop them instantaneously. In fluidics, we work with really low Reynolds numbers, and so you get laminar flow mixing only by diffusion. And it turns out that it's very easy to predict exactly how fluids are going to flow when we are looking at low Reynolds numbers in microfluidic devices. And in terms of electrostatics, we have to think about the fact that small dimensions and feature sizes will produce very large electric fields at very low applied voltages, right? Since the electric field is equal to the voltage over the distance, right? And since the distance is getting very small, if we still put a large voltage on the order of volts that we might think about putting across any given larger scale device, we can get very, very, very large electric fields over those small distances. And in terms of mechanical forces, we have to think about the fact that thin films and micromachine structures have different material properties at these very small scales. in terms of more broadly, we have to think about the fact that atomic forces can become very significant at these super small scales. So two planes of crystals can stick together permanently if you bring them together, and might never be able to be separated, even though you never heated them up or in any other way tried to permanently stick them together. So, and in terms of optical properties, we can now fabricate things that are on the order of a fraction of an optical wavelength, which is pretty incredible. And so you have to think about the interaction with light at these scales, which will then depend strongly on the thickness that you build some kind of mirror or transparent structure. And here are a couple interesting videos on YouTube that you can check out about MEMS devices. Now let's move on to talk about microfluidics. Previously, in the previous lecture, we talked a little bit about why we would be interested in microfluidic devices. So the small size of these devices again means that you'll be able to use very small samples, amounts of sample or blood or whatever it is that you want to analyze. You can get down to single cell interactions. You can use small amounts of reagents, so it's cheaper to operate. You get a very fast response out of these devices because it doesn't take long for chemicals to diffuse across them. You can also potentially implant them in living people. So why fluid? Why are we interested in microfluidics in particular? Well, of course, the body itself is predominantly fluids, and it also means that it's easy to easy to transport samples. In particular, for example, if we want to modulate the environment or measure the things about the environment of a cell, we want it to be suspended in some kind of fluid. And so why microfluidic devices? Well, they're very reproducible now that we have the ability to fabricate them using integrated circuit type techniques, and they have very low production costs, can be easily they can be made cheap enough, and they can be disposable. So because of this, the innovation of making them out of PDMS material. So here's one example of a microfluidic device that we'll come back to a couple times throughout this lecture. And this is a device that Franz Baudenbacher came up with back in the early 2000s, and they called it the nanophysiometer. So it was Franz and Dr. Wixwell came up with this. And it's a microfluidic device in which you can suspend a single cell that you want to interact with and control its environment and analyze its oxidation, etc. So it's got several features to it. One feature is that it's essentially got these the main feature is that it's essentially got these two layers or levels of microfluidic channels, one in which the actual chemical agents and the cell actually live. The idea is that the cell would actually live in this tiny sensing volume, and you'd be able to flush in, flush out different chemicals into it and control its extracellular environment very precisely. But then it also has this really interesting feature of having this second level of microfluidic channels that are essentially valves that can close off the lower level of channels. And we'll talk a little bit about these later. But the idea is that these can you see these three valves across here, across this one channel, and by doing these doing these one after the other, by inflating these one after the other, you can actually create a peristaltic type pump, and to push fluids towards the cell or suck them away from the cell. And so what Dr. Baudenbacher showed was that they could put, for example, a single liver hepatocyte, that's a single liver cancer cell, into the sensing volume channel right there, and both control and sense its environment. And so then they also have these interdigitated array electrodes that they put next to it, that they put adjacent to it, that could then do electrochemical type detection of analytes depending on each electrode's coding. So they could do both amperometric and potentiometric recordings of things like oxygen uptake and acidification. So now let's talk a little bit about flow of fluids through such small devices. So let's think about this setup where we have a pipe and we have different pressures on each end of the pipe, and then we have some velocity of fluid through the pipe. So earlier in 271 we defined the flow as being the cross-sectional area of the pipe times the velocity of the fluid through it. And of course that's equal to the change in volume per unit time. So then the flow is going to be the flow is also going to be proportional to the change in pressure across a given pipe. And then if we think about this like an electric current, then we can write that the flow, which is like the electric current, is equal to the change in pressure, which is like the change in potential across a given pipe, divided by the resistance of that pipe, the flow resistance of that pipe. And so if we have a straight pipe, then we can define the resistance actually mathematically in this way. So the resistance here of a given pipe depends on its area, it depends on the viscosity of the fluid, that's eta, and it depends on the length of the pipe, that's delta L. And so we can see that just as in Ohm's law, if we have a pipe with low resistance, then we get large current or flow flowing through it, whereas if we have one with high resistance, we get low flow through it, and it behaves linearly. Now this eta number, viscosity, this is a parameter that describes the amount of friction between nearby regions of fluid that are moving at different velocities. And the way to understand this is essentially that what it does is it predicts the force, the viscosity, predicts the force that you'd have to apply to one layer of fluid to push it at a given velocity with a given plate that has a certain area A here. So it describes, essentially helps you characterize the force that's necessary to overcome the internal friction of the energy, which causes, of course, then subsequently a dissipation of energy if you apply that force. And let's see, a Newtonian liquid is a liquid where the particles move with a constant velocity due to viscous force. Now from the viscous force equation, it turns out that we can derive an equation for the velocity distribution as a function of radial position on the cross-section of a given pipe. So here, that's what we're illustrating here. And it turns out that the velocity is actually parabolic through this pipe. And so what we're showing here is essentially a cross-section of a pipe. We're showing the velocity as a function of radial position. You can see that in the center, where r equals 0, we have the maximum velocity, and as we move out, we get to lower and lower velocity because it comes closer and closer to the sides of the channel. And so you can equivalently then plot this as these isocontours of velocity if you look at this head-on as the head-on to the flow. And mathematically, the velocity profile is given by this equation, where we have the change in pressure across the pipe divided by a term involving the viscosity and the length of the pipe times the radial position, the difference in the radial position between the given position r squared and the maximum position. So this is the radius of the overall pipe. And so a flow, we know previously that flow is defined as the cross-sectional area times the average velocity. And so that allows us to then calculate the average velocity from this equation as this. And in microfluidic devices, we have what's called laminar flow. And laminar flow in a channel means that there's this velocity gradient as you move from the center of a tube, for example, to the walls, where there's this greater viscosity due to the shear forces that are present at the walls. And so what we have is these side-by-side flows at different velocities through the microfluidic channel. So the amazing thing about laminar flow is that we get mixing only by diffusion. So we get only diffusion mixing. And that is governed by this equation, the diffusion equation. So in this equation we have K sub B, that's Boltzmann's constant, T is the temperature in Kelvin, and then we have other terms involving the viscosity and the particle radius that is diffusing. So then from those terms we can calculate the diffusion constant of a given particle. And it turns out that then if we know that, then we can calculate the distance that particle might travel in a given interval of time, t. And so then delta x here is the radius that it might move within. And this n term is either 2, 4, or 6. So this is n, and it appears here in the equation within the square root. It's either 2, 4, or 6, depending on whether you're looking at one-dimensional diffusion, two-dimensional diffusion, or three-dimensional diffusion. And essentially what this tells you is that if you want two fluids to mix in a microfluidic channel where you have laminar flow only of a given length, you have to make sure that the flow is low enough that the particles spend enough time in the channel that they can move the whole diameter of the channel by diffusion by diffusion only within that time that you give them. That's dictated by the flow rate. So here's another innovation come up with by the Whitesides group at Harvard. So what they showed is that by exploiting the properties of laminar flow in microfluidic channels, they can actually do what's called the selective patterning. So what they can do is they can put two different dyes through a channel, for example, and they can get them to flow side by side. But something perhaps more useful is that they can actually do chemical etching or wire deposition using this technique where they put two chemicals side by side flowing through this channel, and they react, of course, only on their surface, and then they can deposit, for example, a wire electrode on the bottom of the microfluidic channel that is very small, that is only and exists only at the interface of those two chemicals. Equivalently, on the other hand, they could also etch, for example, only a very specific area if they'd like to do that. So this gives you, this technology could potentially then be used as just another degree of freedom, essentially, in lithography and photolithography. So here are a couple example diffusion times of given different particles that we might have in a microfluidic device. And microfluidic channels are often on the order of, say, 10 microns, so what we're interested in is how long would it take these different representative particles to diffuse across the width of a given microfluidic channel, which might be on the order of 10 microns. So here's, for example, a 0.5 micron sphere of whatever substance. So that guy would take quite a long time, 100 seconds potentially, because it has a relatively low diffusion constant. Whereas if we're looking at a protein like hemoglobin, it's going to go a lot faster. It has a much higher diffusion constant, and it can only take a second potentially. And if we are looking at a very small molecule like a fluorescein, then we can get something even smaller than that. So 0.2 seconds or 200 milliseconds we can get. So we get essentially these very different diffusion times depending on the size of the object, its viscosity, etc. And in microfluidic devices, we have what are called low Reynolds numbers. So these are Reynolds numbers that are less than about 1. So Reynolds numbers it's a number that's used to characterize how turbulent flow is, and it's given by the rho, the density of a given liquid, its viscosity eta, the diameter of a given pipe through which the fluid is flowing, and then the velocity of the flow. And you can see that the Reynolds number depends if for a given size pipe, a given fluid, and with a given density and viscosity, your Reynolds number is going to depend on this velocity, right? So if you have a much larger force pushing on the fluid, so you get a much larger velocity, you can get much more turbulent flow, and so then you'll get a Reynolds number much greater than 1. So this is just a sort of an illustration showing like a fluid flowing through this pipe, and then you have this dye, and you see whether the dye flows essentially in a laminar kind of way, or whether it starts to mix turbulently with the fluid it's flowing in. And that depends on the Reynolds number. So what influences the mixing in general? Well, mixing can be adjusted by varying the flow velocities, right? So here's an example of two microfluidic chips, and so you can imagine that you can see right away that this chip has got a lot more length to it, right? There's a lot more length to this channel. So if you get the same flow rate through either end of these two chips, through the ends of these two chips, then you're going to have much higher velocity through this chip than you are through this one. You can imagine that you might get much more mixing through it. So you can do really interesting things with this phenomenon. So you can do things like inject different dyes or different different chemicals together and get different concentrations at different points. And you'll be able to predict very precisely what the different concentrations and mixtures, essentially, of these chemicals are going to be at different places in your microfluidic device. So here's just an example where they're demonstrating this, where they put 100% red dye through one channel, 50-50 red-green dye through another, and then 100% green through yet another. And they're able to get these gradients across the device, right? And then when it comes out, then they get this nice smooth gradient across the final microfluidic channel. So this allows you to get some really precise control over the different chemical variations in the extracellular environment, for example, if that's something you want to control. And so in that case, what you'd be interested in doing is creating these precise biomolecule gradients. So here's another example of a gradient mixer where you get a less continuous distribution, but more of a discretized distribution of these biomolecule concentrations. And so then you can control them much more precisely and get these different discretized sorts of levels of this biomolecule if you wanted to do that. So when microfluidic devices were first being developed, they started to do them in glass. Now glass, in the way that they could do this was they could, for example, take a wafer of glass, they can coat it with photoresist, apply a mask, lift off, then etch the, or remove the non-exposed or the exposed photoresist, depending on whether it's positive or negative. Then they could etch it to form some kind of microfluidic channel, and then they essentially put another piece of glass on top, and then what's left then is a channel wherever they have etched previously. So this is what they did, and they had to heat it up, of course, and squeeze the air out, and to finish it off. And so the nice things about this was that it was compatible with silicon fabrication. They were transparent, insulating. They were probably quite biocompatible. They had low autofluorescence, and they might have been cheaper than silicon. The downsides of this, though, was that they were somewhat amorphous, and they were incompatible with high temperatures. You could start to get them to melt at high temperatures. So one of the key innovations that happened in this field was the introduction by this Professor Whitesides at Harvard, who showed that you could also make microfluidic devices using a material called PDMS, which stands for polydimethylsiloxane. And it's essentially this great cheap stuff that you can buy off the shelf, and you know exactly how it's very cheap, it's very accessible, and it's also very well studied in terms of how it reacts with what its biocompatibility is essentially. And so this is an illustration showing how you would mold PDMS. It's essentially a rubber. And so what you do is you first on some substrate you create your channel, essentially a relief of the channels that you want to create in the PDMS using conventional photolithography techniques. Then you cast this PDMS material on top of that, and wherever you have the notches, or essentially wherever you have the ridges of the channels that you wanted to create, that they are pushing up into the PDMS. And so when you peel it off after curing it, then you get the channels that you wanted in the first place. Then you can take the PDMS and lay it on top of a piece of glass or other PDMS, whatever you want. Drill some holes down into it, and you've got your microfluidic device. So again, here's how this would be done. So you have, for example, your mask design. This is the mask for the nanophysiometer that I talked about earlier. Or this is for the control channels of the nanophysiometer that I talked about earlier. That is a multi-layer microfluidic device. So here's the idea: is that you take maybe a slab of silicon, you expose and develop your photoresist in the pattern of channels that you want. Then you cast your PDMS on top of that those channels. Then you cure and peel off the PDMS, and then you've got your channels in the pattern that you want them. So the other innovation that really allowed microfluidics to take off was the development of this SU8. This SU8 photoresist that was developed by IBM in the late 90s. And so what this really did was allow researchers to create structures with much higher aspect ratios. So the idea is that this SU8 photoresist has a high transparency, low secondary scattering. Here's its optical absorption spectrum, and you can see that where they actually do the application of the UV application of the light in photolithography, you're only catching the tail end of its absorption spectrum, and so you get the low secondary scattering because there's not much other spectrum to be hit by the light. And so then that allows you to get to very large exposure depths, and so you can get very large aspect ratios then, which means you can make very tall structures, which you need in microfluidics in many cases. Okay, so let's then talk a little bit more about that nanophysiometer. So earlier I talked about how it comprises two layers. It comprises a fluidics layer where you actually have the cell you want to manipulate and measure, and you have different channels that you can flow in, flow out different chemicals. And then you've got on top of that a control layer that essentially allows you to create pumps and block off flow in different ways through the fluidics layer. So the idea is that all you do here is just put water or something else through these different channels and cause them to expand and cut off these channels. So here in actually fabricating it, what you do is you create a relatively thin fluidics layer and then a larger control layer just so that you have some mechanical stability, so you have overall a tall device. and then the membrane in between allows you to is flexible and is thin, and so if you increase the pressure in these channels, that membrane will push down and choke off flow through the fluidics layer. And here the device again, you can appreciate again now, perhaps in more detail, the valves, the control layer, and which comprise these what would it be, 8 different valves here that you can control, and then the actual fluidics layer that contains the analytes and the cell and that you're actually interested in manipulating and sensing. Okay, so that brings us to the end of our lecture today. I did want to bring up this one last example of a chemical actuator. So earlier we talked about electrostatic and thermal actuators in MEMS devices. So here's an example of a chemical actuator, and this is what's called a hydrogel check valve. So you have this in a microfluidics device. So you have PDMS structures here and here, essentially these channels. And so if you have some inflow here that you want, or some inflow, outflow, these 2 different channels that you might be getting flow coming out of the device from, you can put up essentially these hydrogel posts, and they exhibit different hydrogels exhibit different physical properties and respond to specific chemical stimuli. So the whole idea of this is that of this particular device, or this particular embodiment of this, is that you'd have these posts, these hydrogel posts here. And if you had fluid running by here and you applied some kind of chemical trigger, if you actually added some chemical trigger to that fluid, then it would cause the hydrogels to expand and choke off the flow through this outflow channel. Whereas if you remove that chemical stimulus, then they'll open up and you'll get fluid flowing again. So this is an example of a chemical actuator. And it's pretty cool because all you have to do is just add some chemical to the flow, to the fluid going through it. Of course, you'd have to make sure that chemical doesn't actually modulate your experiment, but you wouldn't have to apply any other external voltages or anything like that to make these actuators actuate. And interestingly, these devices mimic the behavior of biological check valves and vanes, which also respond to chemical triggers.